All right, hello. If you are watching this video, you probably missed me at AGU or were not attending AGU, but would like to revisit my work and see my progress. Before I actually show you my AGU poster and go through that, I just wanted to guide all of you to my personal website in which I have uploaded all my past work. So you can type in poojashibam.com or include the Squarespace if you'd like. Go to the presentation, publication, and poster tab. And here you can see all my past work, presentations, things that are recorded, as well as publications. And so all of them are accessible through a separate tab. You can download them, and this is to make things accessible for users so that you don't have to actually get a LPI membership. You don't have to get a GSA membership. You can just get that directly from my website. Alrighty, so to get started, I just want to say that this presentation is a continuation of my PhD work, which is investigating the mineralogy of Hawaii drill core. These are rocks and core recovered over 1 kilometer below the surface. And the cores themselves are a part of a much larger project to investigate groundwater and geothermal resources for the state of Hawaii. And I'll be incorporating some of that data here in this talk as well. For this poster, I am just focusing on 2 of the 3 drill core, and I'm going to delve into all the new data collected, and I'm going to relate that to Martian geology. So with that, I just want to warn everyone that I will be zooming in and out of the presentation, and so if you are sensitive to motion, just a warning. And so to get more into this, I want to start by delving into why we are doing this work and why this is a component of my PhD. So a large part of planetary science is using Earth-based geologic settings to describe what is going on other planets, Mars being the most popular destination. Because of current observations on Mars, be it surface expressions of water, so we see deltas and rivers, or spectroscopic observations of aqueous minerals, there is no doubt that water was once stable on Mars. Additionally, many of these secondary minerals are detected in crater walls and crater floors, which indicates some form of subsurface origin. And this idea of subsurface mineralogy and or secondary mineralogy is providing growing support of water being of subsurface origin, so being groundwater. So I even provide an example here on the diversity of the types of secondary minerals that we are detecting within craters. Now this is Columbus crater, which is roughly 100 kilometers across in diameter, and these little pockets of identification are roughly 10 kilometers. And we can see just within the 10 kilometer spatial extent that there is secondary heterogeneity, meaning that there's a diverse set of secondary minerals. So now Hawaii actually has long been used as an analog to Mars because of the similarities of basaltic formation and composition. However, even though we have growing support of Martian groundwater, most planetary analog studies, especially on Hawaii, focus on sampling on the surface or near surface. Here I provide a summary of past analog studies done on Mars and just to point out sampling discrepancies and biases among analog work on Hawaii. So we start by surveying the core using a shortwave infrared instrument to determine the alteration mineralogy of the core. For the PTA, which is right here, we survey the rocks that are within this regional aquifer that was discovered during drilling. The dominant mineralogy is going to be rather low temperature and near neutral pHs, with minerals like saponite, ittensite, and zeolites being detected in the short wave. We can see that there's some zoning with the zeolites here and where the saponites are, but there's no detection correlation between temperature, pressure, acidity, or anything like that. I want to add that the PTA well is warm, with the bottom of the hole reaching temperatures around 110 degrees Celsius. Currently, it's being monitored for geothermal resources, but just wanted to state that it is warm on the bottom. There is no evidence of spectral methods of higher degrees of alteration within the PTA core. Now, the KMA is drilled right here, which is west of the PTA. And the goal originally was to target that western flank of the aquifer. The hydrologist, using geophysical data, thought that would be a way to find the westernmost extent of that aquifer. Now, what is interesting in the KMA is that instead of confidently identifying a regional aquifer, what happened during drilling is that the KMA was within multiple confining units of water. And amazingly, with visual inspection and the spectral survey, we can actually see that, as you see here. The KMA visually can have layers of either superfine grain ash, lower porosity and or permeable units, followed by alteration. And I also want to add that the KMA is also drastically different from the PTA core with regards to alteration mineralogy, with jarosite, palyonite, and hematite being mainly detected, with some instances of saponite. Now, it is currently hypothesized that the KMA and PTA are likely confined to their own local environment, with the PTA core itself being within this dike-impounded aquifer, and the KMA being more influenced by intrusions, ash, and explosive units, all of that can cause vertical and horizontal networks of confinement. Now we want to confirm these findings in each of the individual cores, and most importantly, related to Mars. We do that by using high-resolution imaging through SEM. We also validate mineral end members using XRD. And finally, since we have elemental abundances from Mars, we also want to see how those data sets compare and inform us on geochemical cycles. So I'll start with the SEM imaging with the PTA here on the right. We visually inspect samples that and did not see much alteration past olivine. I provide an example of olivine being altered here with some clay surrounding it. There are some instances of glass being altered, but it was rare, and again, mostly at the bottom of the hole. In fact, the ground mass is relatively intact as seen in both of these images. Speaking of the bottom, we were able to detect some quartz within vugs and veins that were infilled with clays. I provide an example here of some amorphous blobby looking quartz within this infilled vug, and again, that ground mass being relatively intact. And this is our only indication of higher degree of alteration, as quartz is a higher temperature phase. However, and we are also able to confirm these visual findings in the XRD, but again, there is nothing past that indicates a higher temperature of alteration. So moving on to the KMA over here, this is really interesting to look at, not just in the SEM, but also the XRD, which raised a lot more questions. Visually, we see here an olivine being altered to a sulfate mineral that also has some high silica components to it. And then there's also evidence of high degrees of alteration. Here is a pyroxene with spectite minerals, clay all around it. This is a rare occurrence, by the way. The pyroxene being altered is not reflective of the entire core, rather just a sporadic instance in which we found higher degrees of alteration within a sample. Now, the XRD was rather puzzling because, at least with the PTA, it was rather consistent, but with the KMA, we have all this visual and spectral data showing us sulfates being pervasive, but we have very few instances of it actually showing up. And of course, opal, a mineral we don't really detect in the shortwave and don't really see in the SEM either, is showing up to be pervasive, especially in unaltered layers. And so moving on, we use XRF data to not only inform us about geochemical changes, but also to see if it's comparable to Mars data. The PTA, which is in teal over here, has more clay abundance and actually stays within the unaltered basaltic realm. Altered layers do trend downward, so that tells us that this may be a closed system with no real evidence of atmospheric interactions. The KMA is tough because the presence And the KMA also here is in black dots. And this is tough because the presence of sulfate suggests that volatiles were introduced at some point, but we do not detect much sulfur present in the unaltered basalt, so it didn't come from the host rock to begin with. But with that being said, this also just may suggest that alteration may not be as dominant in the core as we once thought. The XRF data is something I do plan on looking into more. So I do want to spend a little bit more time talking about the variability in detection in the KMA and how that may pertain to Mars. I made a table here that has samples that had good amount of sulfur present comparative to the rest of the core in XRF and cross-reference it with the shortwave spectra and XRD data. Overall, the message is that even if we detect these things in spectroscopy, does not mean that they're within detection thresholds of other analytical methods. This is something that we are continuing to encounter on Mars, where remote instruments like PRISM may detect strong signatures, for example, carbonate. But when we send a rover to that area, the concentration may not be as high as we once perceived or detected. So all in all, to conclude, the drill core reveal a lot of things in both the Earth and planetary context. The Hawaiian bedrock is rather homogeneous, being a mafic basalt, but the subsurface is showing us that it is a complex and dynamic environment, which is a consequence of past and current volcanism. In the context of Mars, both these cores are good analogs. There is no evidence of alteration past olivine, which tells us that these reactions are relatively new or short-lived. Most importantly, the types of heterogeneity in the Hawaiian subsurface on a small spatial scale tell us that these types of instances can also happen on Mars within the subsurface. So prior to exposure, groundwater can interact with the bedrock on a diverse scale, depending on regional geophysics and geochemistry. I want to thank you all for listening and participating in my presentation. Please do not hesitate to reach out to me with any questions or comments.